OptWastewater can be applied to real-world regions to find the optimal configuration of their wastewater systems. It takes into account all the relevant economic and environmental concerns. The following tutorial will show the application of OptWastewater. A small example to mimic a real-world situation is used. The objective of the approach is to find a minimum cost solution for the region, subjected to water quality constraints in terms of dissolved oxygen.
OptWastewater has been developed in the Windows environment, using the computer language Visual Basic. The program folder contains subfolders where the inputs and outputs can be accessed. Other data, such as cost functions, can also be edited. The first step towards solving a regional wastewater system is to collect all the required information about the problem. This is done through the use of an Excel workbook. This file is saved in the data folder of the program. The file has 4 sheets with different information. The first sheet has information about the nodes. In this example, there are 25 nodes. The first column contains the nodes enumeration. The second and third columns contain the coordinates of the nodes. Then, there are columns with information about their elevation and population. For each node with population, there is also information about its wastewater generation rate. Nodes without population either correspond to intermediate nodes or wastewater treatment plants locations. The last 3 columns contain information about the treatment plants. If the node is a treatment plant possible location, the respective cell has value 1. If there is an existing treatment plant in the node, its maximum capacity, in terms of served population, is given in the next column. The last column contains the maximum capacity of a possible treatment plant, whether it is new or corresponds to the expansion of an existing one. The second sheet contains information about all the possible sewers between the nodes. The columns correspond to the starting node, the end node, and the distance between them. For instance, node 1 can be connected to node 2, node 6, and node 7. In this example, there are 123 possible links between nodes where sewers can be installed. The third sheet contains information about the initial solution from which the program begins its search for the optimal configuration. Only one sewer can start in each node. The sheet specifies all the sewer's start nodes and end nodes. Also, there is a column to identify its Manning-Strickler coefficient, required for the hydraulic model used by the program. The last 2 columns in this sheet relate to the diameter of possible existing sewers and the peak flow of any pump station existing in that node. The last sheet has all the information on the river, which in this example has 5 reaches. The rows in the top contain information about the main river, such as the river flow and the initial values of its water quality indicators. These rows also contains the water quality indicators for the river's tributaries. The flows of the tributaries are defined in another row. They are considered as extra flow and are added in the reach where the tributary is located. There is also information about other characteristics of each reach of the river. The first 3 rows contain the length, the number of elements considered, and the respective node of the treatment plant. The nodes of the treatment plants were indicated in the first sheet of the file. Other information required about the river is the temperature, the river cross-sectional area, the respective width, the river slope, and the extra flow, as mentioned previously. The subsequent 4 rows define the minimum or maximum values for the water quality indicators. These values are defined by the user to represent the water quality constraints of the problem. In this example, the water quality of the river is defined in terms of dissolved oxygen. Its minimum value is constrained to be larger than 7.5 milligrams per liter. This is required in all the 5 reaches of the river. The remaining rows define secondary parameters. All this information is required for the water quality simulation model that is incorporated in the program. After define all the inputs in the Excel workbook, OptWastewater is ready to be executed. Here is presented the single objective version of OptWastewater of cost minimization. The first step to run the problem is to choose whether the study considers or does not consider the water quality in the river. Then, the data file can be opened through the File tab in the top left corner. A dialog box is presented to select the respective file. The window elements become enabled and the problem is ready to be executed. The algorithms required for solving the model are selected, and the simulated annealing parameters can be defined, including the number of seeds desired to be run. At this stage, it is possible to see the initial configuration of the system. This can be done going to the File tab. In the new window, the initial configuration is shown by pressing the button Design. The 3 sewers and 1 treatment plant that are already existent in the problem are considered in the initial solution and are displayed in red. Now, the program is executed by pressing the button Run in the File tab. On the left of the window, the status text list displays the current status of the problem. On the right, another text list presents the main results obtained while running the program. The progress bar also shows the progress of the problem solving. The simulated annealing algorithms have been applied with remarkable results to several hydraulic system planning models. The algorithm starts with any initial feasible solution, the incumbent solution. Then, a candidate solution is selected at random in the neighborhood of the incumbent solution. Candidate solutions better than the incumbent solution are always accepted, becoming the new incumbent solution. Candidate solutions that are worse than the incumbent solution may or may not be accepted. This is important because it helps the algorithm to avoid getting stuck in local optima. The transition between solutions is regulated according to a cooling schedule and a parameter called temperature. This is shown in the right text list of the program. The algorithm proceeds in a controlled manner until the value of the solution ceases to increase. Then, the local improvement procedure is executed. In this example, the program took just over 1 minute to reach the optimal solution. The cost of the initial solution was reduced in more than 10%. As expected, the minimum concentration of dissolved oxygen was guaranteed. It is now possible to take a look at the optimal configuration of the solution. This is done by selecting the final solution and pressing the Design button. The solution takes advantage of the previously existing system. The existing treatment plant is expanded and 2 new treatment plants are installed. In the File tab, it is also possible to save the outputs of the problem in Excel format. This is done through a dialog box, required to select the names and locations of these files. By default, the files with the results are saved in the Results subfolder of the program. Here is the image with the configuration, as seen previously. All relevant outputs of the problem are saved in the 2 Excel workbooks. The first file includes information about the sewer's configuration and the different costs of the solution. The first sheet of the file has the output for the initial solution. The output for the final solution obtained is contained in the second sheet. The rows in the top have information about treatment plants and reaches of the river. For each treatment plant possible location, There is a column with the wastewater discharged if there is a treatment plant installed. The remaining columns have a summary of the water quality indicators of that reach. In particular, there is information about the minimum concentrations of dissolved oxygen and maximum concentrations of nitrogen and phosphorus. Then, there is information on the sewers, the start node and the end node, the sewer length, the wastewater flow, and the resulting diameter of the sewer, the sewer's Manning-Stickler coefficient, and finally, the diameter of previously existing sewers. The rows in the bottom contain the cost of the different facilities as well as the total cost of the solution. These costs are divided into capital costs, operating and maintenance costs, and total costs. They are also separated for new facilities and existing facilities. In this example, the capital cost of the solution is 14 million euros, the operating cost is 0.8 million euros per year, and the total discounted cost is 25.2 million euros. The third sheet contains information about the parameters used and the time taken by the program to find the optimum solution. The second Excel workbook contains information about the river. The first sheet of the file contains a summary of the input data. In the second sheet, the river flow and the water quality characteristics are presented. In addition to information on the water quality indicators for each reach of the river, this file contains the river characteristics for each element of the river reaches. There is information on the flow, chlorophyll concentration, dissolved oxygen, nitrogen, and phosphorus. As this is an Excel workbook, the values can easily be viewed in a graphic output. Let's take a look at the dissolved oxygen sag curve concentration for the solution of the problem. As expected, the dissolved oxygen concentration is always larger than the constraint of 7.5 milligrams per liter. The concentration curve decreases with the wastewater discharges and then recovers along the river. Also, it is perceptible the improvement in the concentration resulting from the flow increment given by the tributary stream. To conclude this tutorial, here is the summary of the solution obtained for the problem example.
OptWastewater has already been successfully applied to several case studies. The computer program is also prepared to deal with different approaches to the regional wastewater systems planning problem. To know more about OptWastewater, please visit our website. Thank you for giving this matter your attention.
Thank you.